Hi, it's Mike Sklash. Welcome to our second webinar on conceptual site models. And today I'm going to be presenting with my colleague Chris Perret. We'll get started. We have about half an hour. Just background, if you weren't on the last one, I've got a bachelor's degree in geological engineering and a master's and PhD from University of Waterloo in Earth Sciences, and I specialized in hydrogeology, which I did research and taught at the University of Windsor between 77 and 94. I became senior hydrogeologist at Dragon in 1992, and I do things like expert work in the U.S., such as litigation and large projects, and I also do that in Canada. And I'm going to let Chris introduce himself.
I am Chris Perry, and I have a bachelor's honors degree in geology from the University of Windsor as well. And I'm a professional geologist in the province of Ontario and a certified professional geologist in the U.S. I've been with Dragon since 1990 and have worked on a number of major projects with Mike. I also work on some litigation projects, remedial investigations, some site remediation, site decommissionings, and some Phase 1 and Phase 2 projects. Go ahead, Mike.
So last week we talked about chemical fate and transport. Today we're going to talk about conceptual site models, and in 2 weeks we'll be talking about groundwater models. And the idea is to get you going in the right direction so you'll save time and money and grief related to groundwater contamination. So if you have questions during the webinar, please email Alan Hahn at the email address given there, ahahn@dragon.com. If we have time at the end, we'll stay on a bit. If you have live questions, we can discuss those. Otherwise, you can email Chris or me anytime at msplash@dragon.com or cperry@dragon.com. So why would we want to discuss conceptual site models? Well, in our years and years of experience in this business, we found that many remediations take too long or are too costly. And this is largely because the site is not well understood. So you start a remediation and you don't really know what the full extent of the problem is. A second reason would be that if you're involved in a litigation related to groundwater contamination plume, it helps you to determine your contribution, if any, to that plume. And finally, it demonstrates your understanding of a site to decision makers. That, as we'll talk about later, if you're talking to regulators, you're talking to a judge, a jury, a client, this is what you use as your tool to explain the problems and the solutions. So we're going to talk today about what is a conceptual site model, why is it important, how do you make it robust, and we're going to talk about a few mini case studies that will show the importance of conceptual site models. So a conceptual site model synthesizes, so a word I have trouble pronouncing, it puts together all the information on a number of aspects of the site, like site history, physical hydrogeology, where the chemicals are, how the chemicals behave, chemical fate and transport, sources and timing of releases, and exposure pathways and receptors. So it puts all that together in a bundle that can have many different forms. It could be a three-dimensional depiction of all this information. It could be a series of cross-sections and maps and tables, and it could have some narrative. And the example that I'm showing there is one we're going to talk about later on, which helps save a client a lot of dollars and a lot of grief. We'll talk about it in more detail later on. So why is it so important? As I said before, decisions, be it whether you're in court whether you're talking to a regulator, whether you're asking for remediation quotes, are not based on what's actually in the subsurface. They're made on your depiction, the conceptual site model. So I'm going to let Chris talk a little bit about his experience with conceptual site models.
So as Mike just mentioned, conceptual site models are important. However, when we're asked to peer review projects, we find that in some cases there's a lack of a conceptual site model. Site conceptual model hasn't even been done. And we also find that there are significant data gaps or deficiencies with whatever has been submitted as a conceptual site model. And essentially the problem really, it becomes a major problem when remedial investigation work has been done. We're at a remedial design stage. Whoever it may be is getting prepared to start with implementation of remediation. So essentially, the bigger problem here is that if it's done poorly or it's faulty, it leads to poor decisions, cost overruns, change orders, missed deadlines, missed remediation goals. So what if the conceptual site model is faulty, poorly done, or missing information? The regulators are looking for the conceptual site models. They've become more focused on the development of the conceptual site models. In some jurisdictions, conceptual site models are required for submittal of certain types of documents, such as remedial action plans. If your conceptual site model is faulty or poorly done, a regulator is going to know that. And it's not a good practice to have the regulators send back response letters that are in essence saying it's a poor conceptual site model. It's a waste of their time, and I think it becomes more difficult, especially if it's a long-term remediation project. It's not a good way to go. The key component of a conceptual site model is site characterization, putting your arm around the problem. And how do you do this? Well, simply you can identify your source area and then begin with soil borings or monitoring wells around that source area and making sure that you're investigating as deep vertically as possible to get beneath that contaminated zone and stepping out horizontally as far as needed to the point in which you are no longer exceeding a specific standard or cleanup criteria. So here's a little simplistic view. This is an example from a peer review project we've been involved with. A simplistic approach, you have a source area, you have your initial borings that are done around the source area, and then you start doing your second round of borings, which some may give you some of the horizontal delineation, maybe not. And in some cases, you'd have to go out and do another round of soil borings to finally get your hands around the problem. And in some cases, what we found is that third set of borings isn't being done. And in essence, what's happening is, as you see in this next slide, it's difficult to draw this dashed line. You need to have the data. You need to do as many borings as necessary in order to show this horizontal distribution. As I'd mentioned earlier, it's horizontal and vertical. You know, these are three-dimensional problems that we're trying to solve. And in some cases, as you can see here, we have a boring that's too shallow. It doesn't really give us any data relative to the vertical extent of contamination. And that's actually from a case study, from a peer review that we've looked at recently, where we were representing a neighboring property, and we were reviewing work that was done on the site in which contamination was coming onto our client's property. And in essence, we started finding these data gaps. And this is obviously a very significant data gap if you don't have vertical delineation. And regulators have been complaining that this is fairly common on a lot of the documents that are being submitted to regulators, that people seem to forget that vertical delineation is extremely important. Again, you want to be able to show the magnitude and extent of the contamination, so you're building the three-dimensional model of where the contamination is, and you've got your hands around that. Again, we're trying to solve a three-dimensional problem. This next slide, we're going to talk about some of the pitfalls of a bad conceptual site model. This is a case study which is going to be broken down into like a cartoon presentation. It started as a peer review. What we have is a client that has a plant, and there was a source area in which there was a significant source of TCE contamination. And after about 12 years of operating and maintaining a pump and treat groundwater treatment system, the client asked for a peer review, and they came to us. The main reason was that the people at the plant had a gut feeling that something wasn't right. In the beginning, the plume was coming from the source area and heading off to the northwest from the source. And then capture wells were installed to pump the groundwater and treat it. And essentially it seemed like everything was fairly straightforward. But one of the things we were tasked to do is to look at the big picture. And the big picture for us means we're going to start looking at everything around our client's property. And that's what we did during our peer review. We looked at the history of this industrial park. Our client's sitting, as you can see in the aerial photograph, it's a substantial industrial park, a lot of different industries. And as we started looking into the history, we found that there were 5 other TCE plumes at neighboring properties. So what had happened is the client continued with doing some investigation, heading off to the northwest. And as we look closely into the history of the investigation, the chemical data and the hydrogeological data, it appeared that the consultant was chasing a very large plume. As you can see, as these dots continue to head out to the northwest, more wells were added. There's monitoring wells and purge wells. So the remediation system was actually being expanded to the point in which there were 8 large purge wells installed at the end. But these purge wells extended a pretty far distance, and the monitoring wells. And this is a pretty far distance from the source when we look at it. And our initial thought was maybe it's too far from the source. The interpretation by the regulator was that the remediation system wasn't capturing the contamination, so that as we moved out we found more TCE, and the idea was that the remediation system wasn't effectively capturing that contaminated water and sending it back to the treatment building. So there was a bit of a disagreement at this point between what the regulator was telling and kind of what we were seeing, is that some of this wasn't making sense. The plume should have never extended out that far based on the timing of the release and the groundwater velocity. So we were headed to litigation. At this point, the state accused our client of allowing the TCE to escape, in essence saying that the remediation system was inadequate to capture the TCE plume. So we were tasked with building a robust conceptual site model. We incorporated the data from these 5 other sites, plus a lot of the soil borings and monitoring wells that had been done by our client in the previous decade. So we looked at all this, and we started really trying to understand what was going on with groundwater flow. And in this slide, you can see we've drawn in some arrows, and essentially what was happening is the natural groundwater flow in a shallow aquifer was heading to the north and northeast. And essentially what we had found out is that the geology was far more complex than what had been in the previous conceptual site model. So what had happened is these other TCE plumes, as you can see based on how these arrows are drawn, these other TCE plumes moved into the area that our client had investigated. And it looked like, when we started piecing it together, this TCE that was coming from other sites was actually out in what appeared to be a down gradient direction from our client's property. So what was really going on is that the previous conceptual site model that had been developed was poor. It caused our client to spend a lot of time and a lot of money cleaning up other plumes from these other industrial sites. And we didn't have an escaped plume at all. So we ended up going all the way to the state Supreme Court. And the state Supreme Court made a decision using our conceptual model. And the good part of the story is we won. In fact, our client ended up being awarded $2 million for all the costs of litigation plus consulting fees. So we had a pretty happy client. Now I'm going to turn it back over to Mike. Thanks.
Thanks, Chris. So Chris has talked about a couple examples why we want a good conceptual site model in terms of, that's the way that you get the right answer in terms of what's going on. But the problem is that no matter how many boreholes you put in, you really only have a small fraction. You only know a little bit about what's going on. It really takes experience to integrate that information. So this is an example of site, and I'm going to talk about it a little bit later, where it was in court, it was an insurance issue, 2 landfills. Eventually, our client was awarded over $100 million related to this site. 160 acres. There were multiple zones that were impacted, multiple aquifers going down 80 feet. When you look at the volume of material that you need to characterize and compare that to what you really know, we had over 100 boreholes and monitoring wells. You only have a very small fraction of that information. So you need to be able to integrate the information. Some conceptual site models are problematic because you don't have complete information. What I found is that frequently people don't integrate types of information that's available, and therefore the conceptual site model is faulty. So I'm going to use an example which is my personal professional growth, as how you want to take a conceptual site model from a preliminary stage to something that's robust, something that will stand up in court that you can defend easily. So this is me back as an undergraduate student. I was keen, didn't know much, had a lot of hair, you might notice that. But I didn't really know much. I just had the basics. I had the literature, the records, air photos, and interview. That's your preliminary conceptual site model. You want to develop that by getting some site-specific information. In my personal growth, I had become wise. I had a PhD, had a piece of paper. Didn't really have a lot of experience, but now I can put lots of information there like geologic data, groundwater flow, soil and groundwater chemistry, contaminant fate and transport. I could bring in a whole bunch of information and put it together and come up with a conceptual site model that is fairly difficult to dispute. But you want to go that extra step. This is me on the right, experienced, less hair, more weight, lots more experience putting together the various components and adding things like geophysics, groundwater modeling, fingerprints, and isotopes. So you've got all this information that you need to interrelate to get a robust conceptual site model, something that's going to be very difficult to dispute. What I like to do is to use independent and complementary data in constraining my conceptual site models. What I mean by independent data is answer the question directly, and I'll give you an example of this in a minute, but from a totally different angle. And complementary data is constrain the answer, but you don't answer the question directly. I'll give you an example of that also. So here's the example I talked about before, landfill in a legal dispute for many years. One of the questions was how far could iron have migrated from this landfill? And it's a very complex landfill. It's got 3 aquifers or permeable zones with groundwater flowing in all directions. And the neighbors, some of the neighbors were suing, and also the regulators. So how do we figure out how far the iron can move? Well, one way is to look at the groundwater velocity. Something we do as hydrogeologists is use Darcys Law, which is how we measure groundwater velocity. So this is a map in the lowest aquifer showing flow directions, and that would give you an idea of how far iron from this landfill could migrate. So what independent data can we use? Well, for example, instead of doing typical hydrogeologic measurements, we could look at the distribution of tritium, which is an environmental isotope. It's a type of hydrogen isotope that's in the water molecules, and we can tell the age distribution of water based on the distribution of tritium in a landfill, and we can tell whether at a certain distance out that the iron was originating from the landfill or not. Or we can use a conservative chemical parameter that comes from the landfill leachate, like chloride or electrical conductivity. These are chemicals that only change in concentration by mixing, and we could use that as an indicator of how far you could expect iron to move from the landfill. So that's the independent data, looking at velocity in a different way. The complementary data are, what's the geology look like? And here we have a picture of Chris actually taking a sample of sediment from the bottom of a ditch at this landfill. And so we're looking at all aspects of things that are complementary, but not necessarily measuring velocity. We could look at when the landfill started, and did the velocity measurements make sense relative to when the landfill started? Or were there iron problems in people's water before the landfill started? So that's what I mean by complementary data. So here's some examples for need for constraint with independent data, and these are related to models. And the first model relates to this landfill, and we're in court, and the regulators had developed a mod flow model, a typical groundwater flow model, but they had put all sorts of holes in the clay zones or in the confining layers where there was no geologic or hydraulic support of that. And when I mentioned that when I was testifying, the judge couldn't believe that the regulators would put this in to make the model work the way they wanted it to work. There was no data to support what they put in their model. So you need to have independent data that constrains your conceptual model. At another site where a consultant used the thickness of the snow as input, recharge input into a model. This was a site in Michigan, and kind of the general rule of thumb is 10 inches of snow is 1 inch of rain, or 10 centimeters of snow is 1 centimeter of rain. And that really affects how your model behaves. And the consultant forgot to check that. So you need to make that calculation, look for independent data to constrain your conceptual model. Here's another one where this was a litigation case in Canada, and conceptual models on the other side changed during the course of the legal dispute. And the first one suggested that a farmer had stored 90,000 liters of farm gasoline in an underground tank. And, you know, if anybody knows farmers, that unlikely that they would leave unexplained 90,000 liters of gasoline unused, let alone having 90,000 liters of gasoline. Then a next version of the conceptual site model had this underground storage tank on our client's property, but then they did geophysics, and we had done a whole lot of drilling, and they could not find an underground tank. So, you know, you're suggesting there's a tank. Maybe you should be able to find it. And then later on, that same case, a new conceptual site model from the other side suggested that it was aviation fuel and not gasoline because it had lead in it. So you need something that's consistent and conceivable. There was no, this was nowhere near an airport, so aviation fuel and that much of it just didn't make sense. So complementary data to constrain your model. And then check again. put all the pieces together, check fingerprints, geophysics, hydraulics, your records, your phase ones, chemistry, and it doesn't fit. Because if you can't make it fit, somebody's going to show your site model isn't acceptable. So this is a case study where one of our clients avoided $8 million remediation that never would have worked because the conceptual site model was wrong, and litigation. So this was a conceptual site model disaster that was avoided. We did a peer review of this site, and basically this is a manufacturing site that produced aluminum tubing for refrigerators and air conditioners, and this is a residential neighborhood where they had individual groundwater wells, and these groundwater wells were contaminated with trichloroethylene, TCE. This property here was known to have trichloroethylene on it. So, the question was, in terms of when we got involved, how much was this going to cost to clean up? And later on, when the litigation came, is this our fault or not? This is what the conceptual model kind of looked like, where you had a sandy zone and a clay zone and a sandy zone. This didn't make any sense at all. And it turns out that they didn't really have a geologist putting together this information. But here's some information that we looked at in the peer review that didn't make sense. So the local aquifer groundwater contour map, this is the aquifer that the residential people get their water from, indicates groundwater from east to the west-northwest, which would have been good because that would have gotten our client off the hook. But they go on to say, however, based on the interpreted geologic conditions, something's wrong with this. And they go on to say that the groundwater velocity in the local aquifer was 2,900 feet per year. That's really outrageous. Groundwater doesn't move that fast. Chemicals don't move that fast. So where was the groundwater going and how fast? And this is something we had to correct fairly quickly. And this is what we came up with in terms of a conceptual site model after putting in, probably it was close to $500,000 of investigation. These darker colors here are aquitars. They don't transmit water readily or chemicals. And these lighter colors are where the water was moving and the chemicals were moving. This is the plant that had some TCE under it. Turns out that was in a perch zone. And the residences are over here on the right with groundwater flowing towards our client's building. What happened was we determined that groundwater in the perch zone, which was very impacted, pinched out along this line here. The aquifer actually came to the surface and never got to the residential area. After putting together our remedial action plan, we understood that the groundwater was flowing in the shallow zone in the direction towards the residences at about 1 to 2 feet per year. And in the local aquifer, it was coming from the residences 3 to 4 feet per year. And that in the contaminated water would never get to the residences because of the geology. And we did a groundwater model which showed us that the impact from the site would never leave the site within a long time, 150 years at least. So our results were that we convinced the regulators that it wasn't our client responsible for the residential issues, and actually there was a similar type of operation that they did point the finger at. Monitoring we did at about $12,000 per year while the plant operated, because we understood the local aquifer really well. They allowed us to only monitor once every 3 years. We were able to focus the remediation after the plant closed and they were decommissioning, and then after a year we got no further action. So instead of $8 million, we monitored every year for about $12,000 and eventually got a no further action. So understanding the site really well. Getting a conceptual model that is believable is what you want to do. So if you were to take away anything from this talk that Chris and I have done, you need to get the fundamentals right. You need to put your arms around the problem and characterize the site right. You need to have a conceptual site model that you use independent and complementary data, if you can get it, to constrain your answer. Then check for consistency. You have a robust conceptual site model, something that you can easily defend if you had to. And then finally, it's important to make the conceptual site model simple so that decision makers can understand your conceptual site model, so they can understand what you want, where you want to go with it in terms of, who's responsible or how you're going to clean it up. And if they can buy into the conceptual site model, then they can buy into your plan for going forward. So if you have any questions, we'll stay on for about 5 minutes and we'll open up the microphones. Also, just wanted to point out that most of the time when we've come into big project and develop these conceptual site models that are robust, they start with a peer review. And if you're interested, we can do that for you and come up with a conceptual site model which will get you to your objectives sooner and less expensively. Our next slightly nerdy seminar is March 24th, which is on a Tuesday at 1 o'clock. So thanks from Chris and me, and I'm going to open up the microphones. If you can't stay, thank you for joining us. If you can stay and have questions, we'll take those.